regarding humans in space and the future of different advanced technologies ranging from nuclear fission to utilization of high-end physics like quantum entanglement and high-temperature superconductors. And all of this spontaneously led him to the Icarus project. He's currently working in the field of plasma jet magneto inertial fusion within the plasma liner experiment project, focusing on the modeling of plasma jet deflection, merging of plasma liner invasion by smooth particle hydrodynamics coding. And he's going to talk to us about Project Icarus and the analysis of the plasma jet-driven magneto inertial fusion as a potential primary propulsion driver for the project.
Thank you very much. Nice to see you all over here. I have a lot of information to convey, and from what I know, not a whole lot of time, so just please bear with me. And before I begin, I would briefly like to acknowledge Office of Vice President for Research at the University of Huntsville for actually paying for all this, my stay over here, and also all the guys from Project Icarus for their support during this investigation. I will briefly start talking about Project Icarus and what it is, what we do, because I'm the only Icarite currently. Everybody else is at the 100-year Starship Symposium. It is a volunteering, theoretical engineering effort to design an interstellar probe. It was founded under Tau Zero Foundation and British Interplanetary Society back in 2009. Currently, we have more than 20 designers from across the globe. We have some students involved as well. Some high-profile people that are our patrons, and we're I think on a good way to making interstellar flight more prominent in the society. There are multiple purposes of Project Icarus. I just picked the three that I found most important. Those are to motivate a new generation of scientists in designing space missions that can explore beyond our solar system, to generate greater interest in the real prospects for interstellar precursor missions that are based on credible science. And I would especially like to emphasize the portion of credible science. And also to design a credible interstellar probe that is a concept design for potential mission in the coming centuries, and to provide an assessment on the maturity of fusion-based space propulsion for future precursor missions. Now, a brief crash course in history of fusion propulsion. I just picked some of the works that I found particularly interesting. Fusion has been researched, as you probably know, since after the Second World War. However, some of the first ideas for fusion propulsion came in the mid-50s, where notable works of Hilton and Engler were kind of popular. They discussed primitive magnetic mirror concepts, and they were claiming specific impulses of up to 500,000 seconds. Then a major milestone in fusion propulsion and general interstellar missions came in 1978. Also under British Interplanetary Society, Project Daedalus was carried out. This Project Daedalus used inertial confinement fusion propulsion system and was theoretically designed to achieve a specific impulse of 1 million seconds and an exhaust velocities of about 10,000 kilometers a second. They were also one of the first, if not the first, people who utilized the concept of a magnetic nozzle, which I'm actually going to be talking about here. Then in the late 80s, Borowski did a nice study on several fusion concepts, and his ICF-based concept, which I believe was antimatter catalyzed, was claiming a specific power in the order of 110 kilowatts per kilogram. In 1989, Centarius also did a comparison paper in which he explicitly, at the end of it, praises the field reverse configuration-based concepts, which I think is an important thing because, as you will see, plasma jet-driven inertial fusion actually heavily relies on the FRCs. During the 90s, Kamash and Lee published multiple papers. One of them was a magnetic mirror system with a specific impulse of about 400,000 seconds. And Theo in 98, 99 published several papers on the plasma jet-driven magneto-inertial concept, where he claimed specific impulse of 77,000 seconds and really high specific powers. So what is plasma jet-driven magneto-inertial fusion? As the name says, we use plasma jets, and it's also a hybrid between a purely magnetic and purely inertial fusion. So what actually happens, we have a 2D representation of it over here. However, we have plasma guns that are spherically symmetrically distributed across the sphere, right? Spherical symmetry. Those plasma guns fire plasma jets that come in towards the origin. As they come in, they begin to merge, forming what is in PJMIF referred to as the liner. Think of it as a plasma piston that actually does the compression of the target. Plasma guns themselves are essentially railguns. It's, if I'm not mistaken, high school physics, Lorentz force, where you have two electrodes, and then anything that generate magnetic fields around them, and anything that perpendicularly conducts electricity between them will actually get shoved out by an Lorentz force. The magnetic portion, so plasma jets provide the inertial portion of the name. Magnetic portion of the PJMIF comes from the fact that the target itself is magnetized. The process of generating the target is where you fire two spheromag plasmoids with opposite toroidal fields that cancel out when they merge in the middle of a nozzle, getting the field reverse configuration. The idea is when you compress field reverse configuration, the magnetic flux actually increases reversely proportional to the radius squared. So you get the magnetic field in the order of megagauss levels, and that significantly improves the fusion process, increasing the efficiency by orders of magnitude pretty much. So now I have a video. This is actually a video from last year, one of the studies that I did. We have you see plasma jets coming in. The color bar is pressure in kilobars. So notice that at peak compression will actually reach 100 kilobars. There it is. So how do we actually utilize this as a propulsion system? Well, we have a nozzle. It's supposed to be parabolic, but for simplicity, we're just, the graphic represents half a circle. So we have a nozzle. The green circles are superconducting magnetic coils. And so it all begins with firing the spheromags from the sides of the nozzle. They come in, they merge in the center, form the FRC. And so the situation that we have at this particular point is essentially okay, so perhaps it's better to cause confusion. So at this point, you would actually fire the plasma jets. So they come in, converge, and as they approach the target itself, we have this situation. So magnetic coils, the superconducting magnetic coils, are initially generating field, say, of this shape. And as fusion starts to happen, the plasma starts to expand rapidly. Because plasma is ionized, it starts to interact with the magnetic field itself, compressing it back. So the magnetic field flux actually absorbs the kinetic energy of the expanding plasma and acts in this situation like sort of a spring. So as the coils try to return to the initial condition, it actually pushes the plasma out. And this is the same concept of nozzle that Daedalus was using. Okay, so the model that I used for this study is fairly straightforward, not nearly as complicated as some people might think. We have plasma railguns and target generation process. All the squiggly lines are just to let you know are the losses in the straight line of the useful energy. And so we have plasma railguns and target generation system. that gives the energy of the target and energy of the liner to the reactor that is essentially the nozzle, so the same thing. Let me show you some equations also. So energy that comes out of fusion is essentially the energy of the target and energy of the liner that goes in times gain. Now gain for this particular study was kept at the value of 50, which is consistent with the current theoretical knowledge. I almost may say conservative theoretical knowledge of PJMIF. So, also notice an important thing, that an important assumption, which is in a large portion true about PJMIF, is that the large amounts of the input energy comes from the liner itself. So initial velocity of the plasma jets plays an important role, as we're going to see later on. So we have the energy of the fusion comes into the expanding the nozzle, and then portion of it goes out. Portion of the energy goes out with the plasma. Portion of the energy goes to heating of the coils. Then we have the energy of the jet, and portion of the energy is actually recuperated from the coils themselves to charge the capacitor banks, and then we close the loop. That's pretty much it. We repeat that 200 hertz at the rate of 200 hertz, and you've got yourself an interstellar propulsion system. So 2 independent analyses were carried out. We explored a lot of the previous PJMIF studies, did a good job of exploring parameters for particular missions, and they carried out their calculations pretty well. However, few of them, if none, actually played and tried to vary the input parameters, trying to see how it influenced the overall performance of the system. So I tried to do that. Try to change the values of gain and the values of the initial jet velocity if the plasma comes in. And the second portion is essentially I carried out 3 detailed calculations for 3 different technological extrapolation scenarios, because we obviously don't have fusion going on, so we have to extrapolate technologically. Assumed mission parameters and required tech parameters, delta V of 0.08 C, which is what Icarus would like to achieve with the first stage, and delta T, or the burn time of 4 years, as I said, 200 hertz, which is 50 hertz less than Daedalus. That also provides some saving in mass and doesn't really affect overall time of flight. And the assumed, for the first analysis, when I varied the initial jet velocity and gain, plasma mass was 1 gram. Constant 1 gram. So here are the results of the first portion of the study. We see this specific power as a function of the initial jet velocity and gain. It's important to mention that this alpha over here that I calculated, that I used, is calculated as power of the jet over mass of the fuel, initial mass of the fuel, because for interstellar mission, the fuel is going to represent the vast majority of the overall weight of the vehicle. So, as you can see, even with conservative things that are, I would say, almost barely a technological extrapolation, that nowadays we could achieve a fairly high amount of alpha. Well, yeah, also keep in mind that we're talking about roughly 25,000 tons of fuel. So when you talk about smaller missions, this alpha is going to skyrocket. We're talking about hundreds of millions. Specific impulse also scales pretty straightforward, linearly with jet velocity, and shows a significant increase also when you play with gain. However, noted that if you're going to go interstellar, it is pretty much necessary to have initial plasma jet velocities higher than 1,000 kilometers a second. And that's something that has been done before. They actually accelerated plasma blobs up to 3,000 kilometers a second. However, those were really low mass clouds. Second portion of the study. So these are the input that I varied. I made 3 scenarios: conservative, medium, and optimistic. Keep in mind that we're not, when I say optimistic, this is not going to happen within 50 years for sure. we're counting in Icarus that it should happen within a 100-year span. So for the conservative thing, we took 2.2 grams of total plasma, so that's including the liner and the target. Velocities of 200 kilometers a second, which is well within grasp of today's technology. And eta is actually a coefficient that has to do with waste heat and calculation of the radiator mass, which I also did as part of the study. So these are the results that I got. We have mass of the fuel in metric tons, exhaust velocities, thrust in meganewtons, specific impulse, power of the jet, specific power. Also, keep in mind this is power of the jet over mass of the fuel. And then heat that's going to, waste heat that needs to be rejected, and estimated mass of the radiators based on the assumption of rate of 50 kilowatts per kilogram of performance with radiators. So as you can see, mass of the fuel goes down significantly as we move toward the optimistic scenario. And it's an important thing to notice that if you're familiar with Daedalus, you would know that Daedalus actually had a total fuel mass of 50,000 tons. So potentially, PJMIF provides more than 40% increase in fuel mass, which is a lot. Thrust and all the other parameters are well in the interstellar range. You could actually probably go interstellar even with the medium scenario. However, it would require, it would take a longer time just because the delta V would be lower. Also notice that even the most conservative option provides very good performance, and we make a case for PJMIF that it would be a good option for precursor missions and manned missions in the midterm future for NASA and other whoever's interested. If there's anyone from ESA that would like to sponsor us, we're glad to take it. Conservative scenario would be suitable for solar system precursor missions, as I just said. Medium scenario is suitable for precursor missions or reduced delta V interstellar missions, like maybe going to Oort's Cloud or Kuiper Belt. And the most interesting by far result is surely the optimistic scenario, where we would have 40% less fuel required in comparison to the old ICF propulsion system. Also, PJMIF overcomes a number of complex engineering problems that are better than the ICF approach, like pellet production, because we have to cryogenically store them. They have nanometer tolerances on sphericity and stuff like that. So the Daedalus also actually, and I found it just really hard to do. They have to cover the pellets in the superconducting material on top of storing them cryogenically in order to achieve the 250 Hertz repetition rate. So also what we noticed during the study is that vast amounts of heat need to be rejected, and that advanced radiator technologies need to be developed, otherwise we're going to end up with 10,000 tons of radiators. And of course, any increase in gain would further enhance the performance. And with that, I would like to take any questions, and thank you for your attention.
Do we have any questions? Yes?
Maybe I missed it, but the fuel's deheating through?
Yeah. I missed it. It's in the paper, but I missed it.
Another question. In your conservative estimate, you have something like, if I remember well, 15 gigawatt of waste heat. And this, I assume, is within your nozzle configuration.
Yeah.
Any estimate on what would be the wall temperature, the inner wall temperature of your nozzle?
I didn't say it's going to be easy. But yeah, I mean, there's a huge amount, and that's what I was referring to the other day when somebody was in the SETI session, I believe, was talking about sending humans to interstellar missions. Even sending probes is going to be a heck of a job. And sending humans, because of the enormous engineering problem that we're encountering, is just really way out there. I mean, it's not going to happen within 200 years at least.
But we have an estimation.
I mean, I don't have a view, but keep in mind also that a nozzle itself would be huge. So we're talking tens of meters in diameter.
But 50 gigawatts of waste heat.
I know.
And that's just a waste heat, huh?
Yeah. However, keep in mind that basically all the whole paper and what Icarus is currently in a phase where we're going through rough numbers, making estimates, and identifying the issues. So this was pretty much the idea was, okay, let's take PJMIF because we do it at our university and try to see whether the numbers would at least work out for us. I mean, can we at least get the performance, and then we're going to get to the heat and everything else. So.
I remember when the first time Carlo Robbia presented the Robbia engine, there was one question on one of the temperature values that he had for the Robbia engine, which was roughly 16,000 Kelvin. And the question was coming from an engineer, so your engine, which requires materials withstanding 16,000 Kelvin, how do you imagine this? And he said, look, I'm a physicist. This is a trivial engineering problem. I'm not imagining it.
Yeah. I mean, when you come down to that, if I may add to that, is purely magnetic confinement. We have tokamaks where you have plasma millions of kelvins in the near vicinity of the walls. So that's a problem within itself. So. Yeah. Okay. Same kind of issue.
I just wanted to ask you a question about the schematic that you showed of how the PJMIF do you have an idea of what was the plasma properties of the jets coming out of this plasma gas in terms of like density?
Yeah.
Because I see you did a simulation.
Yeah. Well, in this particular case, because it's technological extrapolation, it would probably need to be more than what we are currently looking at in the plasma liner experiment. And in PLX, we're starting off with 10 to the 17th particles per centimeter cubed. So that's the initial. And then the maximum density, the compressed target goes up to 10 to 20, 10 to 21.
And the temperature of plasma at the gas?
To begin with, plasma jets, a couple of electron volts. However, the peak compression, you have 8 kiloelectron volts.
And that magnetic field, is that quite critical to the functioning of the...
Yes, it's very much critical.
If you don't have the magnetic field, will you still get a compression?
You will get a compression, but that's the argument that we're trying to make, because it's a hybrid approach. So we try to get the best of both, because magnetic confinement fusion is good at preventing, trying to be good at preventing losses by the utilization of magnetic fields, and the inertial portion really gives you the punch that provides the sufficient density. So we're trying to take a bit of both, so we don't have such high densities as ICF. ICF goes to ridiculous densities. And however, our magnetic fields are much stronger than either ones, and so we can have a smaller volume than either like what 800 cubic meters. And yeah, if you don't have that magnetic field to prevent the alpha particles and electrons of flying away, you're going to end up having huge losses, and it's not going to work. So it's crucial that you have that magnetic field in there, and that's one of the things FRCs have been proven to work. So actually, if you compress them, you'll make them.
Do you have an idea of the strength of that magnetic field?
At peak compression, I didn't go crunch the numbers myself. I read it in the literature. It's in megagauss levels.
Thank you very much indeed.